Okay, we are almost done. We've completed our review slash overview of complex numbers and all of the different amazing things that they do up through the residue theorem. Now, all of that so far has been sort of upper level undergraduate. But what we're doing now, this topic goes way off the charts, and what we're going to learn about now is actually something that you probably won't learn as an undergrad at all. This is getting to be graduate school. So we're now going to lead finally to the Weierstrass equations, which I will explain what they are very shortly. But first we need to go over a couple other things. So the next topic is lattices and doubly periodic functions. So we're going to talk about what a doubly periodic function is, and it turns out that every doubly periodic function is an elliptic function, or an elliptic leads to an elliptic curve. So what is a doubly periodic function? Well, in one dimension, in real numbers, a periodic function is something like a sine wave. It just goes, it literally repeats, right? It has a period. If you multiply it, 1,000,000 times 2 pi, you're going to get the same thing. 1,000,000 times 2 pi in the negative direction, you're going to get the same thing. It's periodic, goes on forever. So that's one dimension. In one dimension, things can only really be periodic in one way. They might be, like, the pattern might have different periods, but in complex numbers, we're talking now about two dimensions, the reals and the imaginaries. Because of that, functions can actually now be periodic in two directions. So you can have, it doesn't necessarily have to be directly along the reals and directly along the imaginaries, but it can be in two directions, two independent directions. So these functions they repeat in two directions. So a real function repeats in one direction. These doubly periodic functions can repeat in two directions. And so what you end up with is, in one dimension, if you have a sine wave, there's a period, right? From 0 to 2 pi, then it's going to repeat. So in complex numbers, you can have two different directions in which they repeat. So if you put the corner of a parallelogram at 0, then the one period might be out here at, call it omega 1. Another period might be out here at omega 2. And this thing creates, so with real numbers, it just repeats along the real axis. Here, it actually repeats in two directions. So what you actually end up with is a lattice. It goes in either direction and multiple times in either direction. It tiles. So what you have is, that with a real function, if you think of sine of theta equals sine of theta plus, let me make sure I get this right, n2 pi, right? If you, whatever your value of theta is, if you add to any multiple of 2 pi to it, you're going to get the same value. So with with a doubly periodic function in complex numbers, you have the same concept, but it goes in both directions. So what that means is that if you have a point here, z, it's going to have the same value if you add omega 1 to it, if you add 2 omega 1, 3 omega 1, this point is going to be the same everywhere. And if you go up or down, it's going to be the same. But also, if you go in any direction, if you go from here down to here, there's going to be a point here that has the same value as this. It's periodic in both directions. So the way that that is expressed is that there is an omega 1 and an omega 2 that defines this parallelogram so that z equals z plus omega 1, z equals z plus omega 2, and then also more generally in any direction, z equals z plus any multiple of omega 1 plus any multiple of omega 2. So you can go any direction, okay? So the next thing is that there are all sorts of, so these functions are very interesting. So a doubly periodic function cannot be holomorphic, meaning it cannot be smooth. It cannot be differentiable everywhere. Which means, another way of saying that is that it has to have a pole at some point. So if you have the function along here, somewhere in here, it's going to have to go up to infinity and back down. That's what a pole is. So why is that? Because if it doesn't go to infinity, then if you think about a sine wave is bounded above and below. It never gets outside of that. There's a theorem which we'll prove later by Louisville, which says that any bounded entire function has to be constant. So in complex numbers, if there's a function that never gets above a certain amount, then the function has to be constant. So what that says is that if you have a periodic function, if it doesn't have any poles, then it's going to be bounded. If it's bounded, it's going to be a constant. So there must be poles in it somewhere. And then we know it can't have one pole because, so the next thing is that at the same time, Louisville says that this can't be constant, or that if it doesn't have any poles, it's going to be constant. So we know that it has to have one pole. But we also know that because it's periodic, the boundary, it has to be 0 around the boundary, because from here to here, it's always smooth. So whatever it's doing in here, it has to go back to 0 and do it again in any direction. It has to be 0 in any direction around here because it's smooth from one tile to the next. So around the boundary, it has to be 0, but the whole function can't be 0. So we know there's at least one pole, but we know from our residue theorem that if there's one pole, there's going to be a residue around this, which means that the value around the parallelogram would not be 0. The only way to have poles and still make it be 0 is if there are at least two poles so that they can cancel each other, so that the function can go to infinity, but also is 0 at the is 0 along the perimeter. So one of these doubly periodic functions has to have at least two poles or a double pole. And we'll get into the details about which is which and so on later. So one just example of this to think about what this means is if you think about 1 over sine squared, I can't even read that. 1 over sine squared z. If you think about 1 over z, so if you think about sine goes to 0, right? So 1 over sine is going to have to look something like, it's going to go to infinity and then down and then, let's see, what would it do? I think it would look like this. Oh, sure, that's the secant, right? I think it looks like this. So the point is it has to go to infinity as it moves up. So if you square that, it's the same thing, but it's going to go faster. And then with the z, it can be in two directions. So that's kind of what it's going to look like. And one last thing is that, so for these functions, there's going to be a pole in here somewhere. And it doesn't matter where we define the lattice, so we might as well put the pole at the origin. Okay, so the next thing that I want to tell you is about TORI, meaning, that's a fun word, of course, the plural of torus. A lattice is the same thing as a torus. Do you know why? Something maybe to think about if you haven't, because it's very cool. But if you go this direction, you're basically going to come back around, right? And end up back in here. If you go this direction, you're going to end up coming in back here. So basically, this line connects with this line. So if you sort of sew it together, you're going to end up with, I guess it would look like a tube, right? And then maybe the seam is here. And then so this point would be here. And then it goes, the circle from here goes around and comes back there and then goes across, okay? But we're saying that it also, if you go this way, it comes down and you're going to end up here. If we sewed those 2 points together, what are we going to end up with? You're going to have to twist it around and you're going to end up with a donut. So then if you go here, if you go off this way, you end up here, right? So if you go off this way, you end up here. So lattices and toruses, tori, are topologically the same thing if you keep going repetitively, or you can just go around in the circle. This then is very similar to what we've talked about before with cyclical groups, if you remember our discussion before about groups. So it's just like a clock, it's just like clock arithmetic. If you add like 10 plus 5, you go 10, 11, 12, 1, 2, 3, right? 10 plus 5 equals 3. It's the same thing with toruses. You go around and you end up back where you started. So we're getting there already because these lattices are the same thing as a torus, and the torus has the same group structure as a clock, although it's in 2 dimensions, because you can go around the clock this way or you can go around the clock that way. So we're very close now to where we started, which is with group arithmetic with elliptic curves, but we haven't actually gotten to the elliptic curve yet. That's what we're going to do now. So now we're finally at Weierstrass. The Weierstrass P function. So Weierstrass knew that these functions, these doubly periodic functions, he wanted to sort of encapsulate or see if he could find just an example of the most basic kind of doubly periodic function he could. So he worked to create an equation that would be a doubly periodic function. And then it turns out that basically all doubly periodic functions can be expressed in this way. So they have to have 2 poles. So as I said before, he has his own letter, P, and P of Z equals. So he wanted to. So I'll explain this later, but I'll just show you what the equation that he came up with is for now. So it's the sum of all the omegas they're elements of the lattice except for 0, of 1 over z minus omega squared minus 1 over omega squared. This looks very complicated, but actually it's not. All the weirdnesses are just to deal with, you don't want there to be a 0. You have to deal with the fact that there would be a 0 here in the denominator. So he just added 1 separately, and then this omega is just to keep it, to make it converge. Without this, it won't converge, but we'll go over this in more detail later. It's actually not that complicated, but that's what this function looks like. This function is basically a generic function for these doubly periodic functions. And then if you take the derivative of that, which I'm not going to actually do this now either, but I'll show you what it looks like. It then is actually even simpler. It's the sum of all the omegas of z minus omega to the minus 3. So that's the Weierstrass P function, and this is the derivative of the Weierstrass P function. We'll look at these more later, but then what happens is he found a relationship with these, which is the Weierstrass equation. He found out that there's a relationship between the derivative and the between the doubly periodic functions and their derivatives. That relationship is that the derivative squared equals 4 times the original function cubed minus some constant, and then minus another constant. And what is this? As I showed you at the beginning of this this introduction, this says that y squared equals x cubed plus ax plus b. This is an elliptic function. So what Weierstrass discovered is that these doubly periodic functions have a relationship that is the relationship described by an elliptic curve. So that's it. We did it. This connects elliptic curves and Fermat's last theorem to complex numbers, which is going to then connect to modular forms, and then we can go back. So we'll look a lot more at this, but this is just it's really fascinating and strange, and you can already see that there's like amazing structure going on here. Just because you have a doubly periodic function, you end up with a relationship between the derivative and the original function that is described by an elliptic curve. That's amazing. Just quickly, I'll write down what the two G's are, but we'll they look ugly, but we'll be able to derive them, I think, without too much trouble. So it's the same thing, except for 0. This one's just 1 over omega to the 4th. The 60 is the weird thing. And then the second one is the G3 equals 140 again across the lattice, 1 over omega to the 6th. And these numbers have to do with as you're taking the derivatives, you sort of add up the coefficients or multiply the coefficients. So that is that is it. We're there. This is really fascinating. And what's exciting to me is that even though I know this stuff looks completely difficult and bizarre right now, I think that after we go through all this, after we learn more about complex numbers, complex analysis, and then we look at these in more detail, you'll see that actually we can follow this. We can understand what this is, and that's going to lead us in a strong way to elliptic curves, and we'll really be well on our way to really learning this stuff. Although we're just getting started. We haven't really started learning anything about elliptic functions or modular forms yet at all. So that is it for the introduction. Now we'll start in more detail with the entire with this entire series, starting with constructing real numbers and then leading up through all the complex analysis and ending here with the Weierstrass function.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.